Welcome to another video explaining the universe using the particle model. Well, today's video is the initial results of my latest experiment, where I'm increasing the speed of the G1 particle through the circuit, in particular through a resistor, and shows that the current drops. But before we do that, here's a little bit of information about the book that Dave and I have written. Yes, the name of the book is Principia Mathematica II, and is available on Amazon in hardcover or paperback, and it's in full color. And you can also get it as an ebook for only $3. So, yes, get to the slide. I've been going through equations. And I guess I need to start changing this to experiments and the analysis of the experiment, because there are going to be a number of videos made, because what I'm doing today is just giving you the results and trying to see if we can say anything about the experiment itself. Previous video was I showed you the graph of three sets of equations: standard equations for a circuit, TPM equations for a circuit, and then TPM equations with a speed factor put in. I described that in the previous video, and today we're going to talk about the initial results. I'm not going to go through this a lot, because I'm going to list the previous video in the description of this video when I release it. But this is the important one. This is where I took TPM equations and I added the speed factor to the sense resistor, the resistor that I'm really trying to test, and another sense resistor. And what I did was I took one resistor and I set the voltage to around 5 and measured it. And then at 10, 20, 15, 20, and 30, and I measured the voltages around the circuit, recorded them, then compare the results to the predicted value. And I went through that for the standard equation, the TPM equations without speed, and this one, the TPM equations with speed. Now, to refresh your memory about this whole point, and is that the G1 speed through a component does affect its interaction. As the G1 current increases, the F2 force around the resistor increases, which increases the average speed of the G1s through the resistor. An increase of speed causes the G1s to pass through more easily. And when they pass through more easily, that means there's fewer loss, which means the voltage drops, which means the current drops. This theory, by the way, helped explain the IV curve of the diode and the transistor. And I've listed this before and put it in the description of the video, and I'll do that again. But this same thing applies, and it actually conceptually helped explain how the shape of the IV curve, for which there is no present explanation. As the G1 enters an object, it speeds up, and then as it leaves, gets halfway through, so to speak, it slows down. And this is true of all objects, whether it's light going through a prism or G1, gravity going through my body. And these are the three predictions. This is all based on a 5 volt. I did it for 5, 10, 15, 20, 30 volts. But when the standard equations say that the current through the sense resistor and the current through the R1 and the current through the second sense resistor, they're all equal. That's what the equations say. TPM without speed says that the current starts out high, gets lower, and then lower. And that's consistent. It loses. G1s get lost as they go through the resistor. They interact it. You lose some here, then you lose some here and there. And so it's always going to decrease. And I've been saying that for almost 5 years until I realized that with speed, you get a different result. And this is a result of my spreadsheet calculation for the 5-volt circuit using, I believe it was 4K or resistor for R1 sense resistors are 1 ohm, and it starts out high, comes down low right about where it would normally be, and then it goes high again. Haven't really explained that curve very well, and I'm not going to do it today because I don't want to take away from the initial effect of the results. This is a prediction. These are the 3 curves. The question is when you measure it. When you measure, you only measure once. I can't measure and try to get this or try to get that or I can only measure once and I get what I get. And by the way, so you know, this is my lab right here in my bedroom. As I'm sitting here, to my left is a bookcase, and behind the bookcase is a card table, and this is the card table, and this is my setup back there. I have a signal generator, which I'm not using for this experiment. I have an oscilloscope, and I'm not using it either, but I am using a power supply, and you notice I actually have it when I took this picture. 15 volts was one of the settings that I had, but the digital multimeter, 7.5 digital multimeter, has to be a very accurate meter to do this. You can see there's 15, and those are all the digits. And of course, this is my circuit. The power comes in on this side. I have a sense resistor here. This is my 4K resistor, and this is my other sense resistor, and then I got a shorted wire over here because I don't need the rest of this board. This is the lab. This is where I did it. It takes about an hour of voltage. So it took them about 6 hours to do this test over a 2-day period. And this is what I got measured. At 5 volts, it started high, higher than normal, went down to normal, and went up just slightly. So there's a not as dramatic as this one. When I jumped it up to 10 volts and did the measurements, the current through the sense resistor was high, went low, and went back high again. And you might ask, well, why does it go high again? I'll get to that in another video. But you can see that it's not a straight line. It's not steadily decreasing. It's more like the TPM equations with speed. There's 15 volts to 20 volts, and there's 25 volts and 30 volts. It looks like it tends to flatten out here, and I haven't analyzed that yet. There's a lot of analysis I have to do anything. The whole point is you look at those 6 curves and you compare them to the predicted model. Here's the prediction. TPM without speed. Standard is the red, and this was the prediction. This was for 5 volts, and this is what I got. Does this curve match this, the red, or this? And I haven't showed you the other predictions at 10, but they were all the same. Evidence. This measured evidence seems to say yes, based on a prediction that an increased flow of G1s through the resistor causes a reduction, causes them to pass through more easily, and hence a reduction of voltage at the resistor. This is the reduction of voltage. This is a reduction. Now, these are sensories. These are only 1 ohm resistors. So they, even though they're being reduced, the effect is not seen as well. It virtually is a test that says, if you believe the equations, if you believe the concept I'm trying to tell you about, if you I shouldn't use the word believe, if you are of the opinion that the concept is solid, the equations are solid, then this is supporting evidence that the particle model equations taking speed into effect is a proper explanation of these measured curves. Okay, so by the way, I've done 2 experiments, one of them almost 3 years ago. And these 2 experiments are not proof. I don't want you to get the idea that we have proved the particle model, because there is no direct evidence that there is a G1 particle flowing through the circuit that behaves the way TPM explains or predicts. But there is indirect evidence, and indirect are the voltage measurements and the current measurements, and those are indirect measurements. So I have verification of voltage, but not of what's really happening with the G1s. I did a 3 resistor experiment 3 years ago. It is in the book. You read Appendix D in the book, you will get an explanation. You'll see that based on the predictions of the particle model that we got a 70 and 80% correlation from predicted to measured, which was I thought quite good at the time, and that is supporting evidence for the model. You can get the results of this also on a video I did, and I'll put that in the description. The second experiment I've done right now is the speed experiment, and of course, both of these are supporting evidence, not proof. Regardless, this is amazing support for the particle model in terms of how it explains the function of a simple DC circuit. Well, there's more to do, a lot more to do. I'm going to do 2 more. I'm going to pick 2 more resistors, go through it so I can have more data. I need more data. I have equations for VG1 IFR, and I got at least a proportionality statement, this thing down here, for the speed factor. And the question is, can I look at the measured data? And can I do anything with the measured data and get a better handle on what these numbers really are? So only time will tell. I haven't done all the analysis. And the value, I may even get a better handle on the value of G2 mass. I had to make an assumption about what the G2 mass of that resistor was and use this equation to calculate a reduction. My calculations are probably way off. I have very extreme graphs that come out, all very V-shaped. And you can see the 5-volt one was not, they tend to flatten out a bit. So my actual numbers are clearly wrong, but they're accurate enough to show the possibility for these things. So there's going to be more. I'm going to do more testing. I'm going to do more analysis, and I will come back with a better explanation of some of that in a later video. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, ask Particle. Thank you for your attention.